Hello, this is Mr. Santry, and this is going to be a quick video describing chemical equations to you guys, as well as what the parts are that you need to know, how to read them, and how to count atoms and stuff like that. Let us get started. So, the first equation that you have is just this whole statement right here, okay? So, basically, a chemical equation is kind of like a math equation, except instead of an equal sign, it has an arrow, like down here, okay? And you guys have done this in your vocab quiz, but in blue, I'm going to circle on the left side of the equation. These are your things that they call the reactants. These are the things that you have before the chemical reaction that change. The arrow, again, represents the reaction itself. So a chemical equation shows you a chemical reaction as it happens. And then in green here on this side, I am going to circle they call these the products, right? These are on the right side of a chemical equation. So on the one hand, on the left, you've got your stuff that you start with, and then you got your stuff that you end with. Some of the things you guys hopefully are already kind of noticing is that first, let's split both sides just with a big purple line here, okay? And then we're gonna count out which kinds of elements we have on both sides, and then we're also going to look at how many of each one. So on our left side, on the reactant side, it looks like we've got C for carbon, right? So C. It looks like we've got an H, which is hydrogen, and it looks like we got an O for oxygen, all right? On the product side, we also have a C, we also have hydrogen, and we also have oxygen. Huh, that's weird. You have the same kind of elements on both sides. This is because of something called the law of conservation of matter. That basically states that you cannot create or destroy new atoms and elements in the course of a chemical reaction. So the stuff that you begin with, your reactants, have to be the same as the products. You can't magically get a new element out of nowhere. And so part of checking to make sure that's true is we're now going to count the number of atoms on both sides of this equation. Okay? So again, we're only going to focus on one side at a time. If we're on the left side of the purple line, we're not going to worry about the right side yet. So on this left side, let's count up the carbon first. So there are two things you look at when you count what's in an equation. One of the things is the tiny number that's next to each element. That is called the subscript, which you should have heard of before at some point, but that's the tiny number. This little 4 next to the hydrogen means that there are 4 hydrogen in this molecule. If you don't see a number, a little number to the right of it, like you see how carbon doesn't have one, you assume that it's 1. So technically it's a C1, but you don't need to write that because it's just assumed with C. So on this left side, we have 1 carbon atom. On this hydrogen, like we just talked about, you have 4. And then for the oxygen, you have to do something tricky. You see this big number now next to the 2? I'm sorry, next to the O? That is what you call a coefficient. C-O-E-F-F-I-C-I-E-N-T. Coefficient. And what this big number next to the O2 says is that it says, okay, you have O2, all right? So I'll draw 1 molecule of O2. There's O2, but since there's a 2 as a coefficient next to it, it's saying you have 2 of those. So here's 1 molecule of O2. Here's another molecule of O2, because you have 2 of those. The big number is your coefficient. And all you got to do to find the total, I mean, you could draw it out like I just did and just see that there's a total of 4. Or you could also take the subscript next to it and multiply by the coefficient to get a total of 4. Alright, Now let's go to the product side. Again, C is easy. We got 1. All right. Hydrogen. Looks like you've got a subscript of 2 next to the H. Multiply that by the coefficient to get 4. And then for oxygen, you got to be careful because it shows up in 2 places here, right? 1 is here. If you don't have a subscript, it's assumed to be 1. So 1 times 2 is going to be 2. But that's plus 2 more over here. And that equals 4. So the next thing we talk about is whether your equation that you have is something that you called balanced or not, but I will continue this in the next part. So as I play forward in the animation, here are the atoms that we already counted. So here's the product side, here's the reactant side, all right? And when we talk about whether an equation is balanced or not, so let me separate this with a line again. You say that an equation is balanced if your atoms on your product side are equal to the atoms on the left side. So if you look at our inventory that we have, each side has 1 carbon, 4 hydrogen, and 4 oxygen. So we would say they are balanced. And again, you want to kind of think of it, excuse my artwork, as a scale, right? Here's one side of the scale. Here's the other side. As long as both sides are equal, right? If you got this guy on this one, and this other guy over here, as long as they're equal, you'd say it's balanced. If you had 2 people over on this one, it would be unbalanced. So like in this one, if instead of 1 carbon you had 16, that would not be balanced at all. So that equation would not be following the law of conservation of matter. Okay, so we're going to balance this one, or look at the atoms like we did for the last one. I'm just going to separate it with a line again, and I'm going to do these by color like they have. So Fe is going to be in red. I'll put it on the other side because you guys already know they should have the same elements. We're going to put C in green. Carbon is C. If you ever don't know these, you can look them up in your periodic table. And then O is going to be in blue. So looking at the iron, we do have a subscript, but look at, you also have a coefficient. So it means of these 2 molecules, you're going to have 2 of them total, so we can take the 2 for Fe, multiply it by 2, and we get 4. So just to give you an idea of what this looks like visually, what the molecules would look like, if you've got 2 Fe, and then you got 3 oxygen for Fe2O3, you have this one molecule, and then you also have a second one, because the coefficient is 2. So there should also be another one. There's the O3 part. And then there's Fe again for 2 molecules. So that's what it looks like. But again, if you count these, you have a total of 1, 2, 3, 4 of the red iron. Okay? And then let's look at oxygen. I mean, hey, I already drew it out. We could count it. So you could see 1, 2, 3, 4, 5, 6. But again, if you don't want to do all that math, you can look at the subscript, which is 3, multiply it by that, which is 2, the coefficient, and you get 6. Carbon's easy, right? It's just right there. You got a 1. If there's nothing, you assume it's a 1. All right. On the product side, Fe is easy for this one, right? Looks like it's just 1. Carbon, if it doesn't have a subscript, you assume it's 1. So that's 1 times 3 for 3. And then oxygen, 2 times 3 is 6. So I want you to just look at this now. Tell me, is this balanced or not? Yeah, it is not balanced. And I'm going to show you very quickly how to do a simple balancing on the next slide, and then you can continue on to your next. Okay. So using what you found in the last step, here's what we have. We decided that it was unbalanced. So if you do ever do this, here's how you balance in a chemical equation. So the first thing to note is that, well, let's just look at these. So on this side we've got 4 iron, on this side we've got 1. You've got to add a number to one of the sides to make them equal, right? What you should never ever do is add a subscript for this like that. So while you would technically have 4 atoms of iron, what you are doing is, this is a regular atom of iron, and when you add a subscript like you, or like I just did right there, you are saying that you have this molecule now. And that's not what you have. You have to keep the composition of everything the same, because a molecule of iron like this is distinctly different from a single one like that. So I'm going to erase this, and here's how you should do it. Just make it a coefficient, okay? So I'm going to write 4 to the side of the Fe like that, and what you're saying is, oh, I still have single atoms of Fe, but I have 4 separate ones. And that's how you can balance it without changing your composition, okay? So now instead of 1, we've got 4. And then likewise on the carbon end of things, you've got 3 on this side, 1 on this side. Just put a coefficient of 3 next to it. And now you've got 3 of those. So that's how you balance it. This was an easy one. They'll get more complex as you go on. But if you follow that, you should be pretty good. All right. Bye-bye.